Section 15.12, the path of a reaction and the effect of a catalyst. Okay, so we've been talking about equilibria and equilibrium constants. The equilibrium constant describes how far the reaction will go. It describes the balancing point between reactants and products. It doesn't tell us how fast it gets there. The reaction rate is what tells us how fast it gets there. You could have an equation, a reaction that could take a year to get to equilibrium. Or it might take a nanosecond to get to equilibrium. It's just all over the place. It's the reaction rate that tells us how fast it gets to equilibrium. And we talked about collision theory in terms of reactions at the beginning of this chapter, and about how in order for two molecules to react, they actually have to run into each other, and they have to collide with enough energy to react. If the collision is too gentle, too low in energy, then nothing happens. They just bump each other and go on. The activation energy is like a barrier that has to be overcome. High activation energy means that you need a more energetic collision. And what that activation energy usually is that you have to at least begin to break the bonds that were originally there before the new bonds can be formed. And it takes energy to break bonds. So we're going to talk about activation energies. So we've got pictures. Pictures are good. So here we have an example of hydrogen gas and oxygen gas. They will react and form water. And this is a highly exothermic reaction. It's downright explosive. Okay, when I was in college at Iowa State University, we had a club called SCUM, S-C-U-M, the Society of Chemistry Undergraduate Majors. So SCUM sounds like a dumb name, but the scum always rises to the top, right? So we would do this show every year, this chemistry show, and one of the things we did is we'd have a balloon with oxygen in it, and a balloon with hydrogen in it, and a balloon with hydrogen and oxygen mixed together. And these, they're floating, and so we took a candle on a stick and touched the flame to the oxygen balloon. It goes poof, and the hydrogen balloon, poof, and then the hydrogen and oxygen together, kaboom, and this big auditorium, all the ceiling tiles lift, and we're like, maybe we should make that balloon smaller next time. It's explosive. But why did it sit there peacefully in the balloon before we gave it the spark? Were the hydrogen and oxygen molecules not running into each other? No, they were bumping into each other all the time. But they didn't have enough energy to get over the hump. So here's the initial energies of the hydrogen molecules and the oxygen molecules. In order for them to react, they have to react with enough energy to get up and over this hump. It's a little bit like playing miniature golf. You have to hit the ball, and it has to have enough energy to get up and over. Otherwise, nothing happens. It just rolls back. So at room temperature, nothing happens. Gasoline. You go get gas for your lawnmower. Put it in the jug and bring it home. Does it explode on the way home? No. It just sits there. It'll sit in your garage for a long, long time. Nothing happens. But you light a match to it, right? And it burns, and you've got trouble. Why does it take the spark? It takes the spark to get over the hump. Okay, there's this activation energy. In order for these things to react and form water, we have to break the bonds that are holding them together right now. And that takes energy. So this is the activation energy. And then the energy of the products ends up being lower. This is an exothermic reaction. In this process, energy is released. The reactants had a higher energy than the products do. But it won't just go from high to low because there's this big hump in the middle. Okay? So that's called the activation energy. When we think about gas particles, they're moving, right? And they have kinetic energy. And we talk about the temperature as being related to the average kinetic energy. But we have fast-moving particles and we have slow-moving particles. So you may have some molecules, if you get a fast-moving hydrogen, well, you need two. No, you don't. Anyway, if you get a fast-moving hydrogen and a fast-moving oxygen that run into each other, they could react without that spark. But the chances of them doing that are pretty slim because there aren't many at that higher energy. There's a lot in the middle. There's a few that are moving really slow and a few that are moving really fast. It's like a bell curve. The higher the activation energy, the fewer reactant molecules have enough energy to get over it without any help. And the slower the reaction rate. If the activation energy is really slow, if the activation energy is just a little tiny hump, then the reaction rate will be faster because more of the molecules have enough energy when they collide. So in general, at any given temperature, the higher the activation energy, the slower the rate. And that makes sense. The higher the hump, the slower the rate. Another analogy for that, I don't know if I have room to draw it here. I'll try to make room. So imagine that you have this fence. It's not barbed wire or electric or anything crazy like that. And you've got these little kindergartners. And for whatever reason, I haven't gotten that creative, they need to climb over the fence. Can they climb over the fence? Yeah, they can, but they're kindergartners, and they're not as agile as Andrew, so it's going to take them a while. The higher the fence, the longer it's going to take all those kindergartners. The slower they're going to go over the fence. The higher the activation energy, the slower the rate of the reaction. Does that make sense? So is there any way to speed up a slow reaction? How could we speed up the reaction of kindergartners going over the fence? We could lower the fence. Or what if the teacher came out and lifted him up and over the fence? Here's the teacher. What if the teacher just picked him up and put him over the fence? Would that speed things up? Yeah, probably. So there's several ways to speed up reactions. Let's see if we can make this work with the kindergartners. Increasing the concentrations. If we have more kindergartners at the fence, will more of them get over? Will they get over faster? Yeah, because there's more going over at one time, right? They're still kind of slow going over the fence, but if you've got a whole bunch of them trying, they're going to go over faster. So increasing the concentration. So back to collision theory, if we increase the concentration of the reactants, they're going to run into each other more often, right? And so there will be more high energy collisions because there's more collisions of all kinds. And so you can increase the rate by increasing the concentration. But if we increase the temperature, so increasing the temperature would be giving these little kindergartners rock stars, I guess. Just like, I'm not advocating that in any stretch of the imagination. But if you pump these little guys up on caffeine or sugar or something, then they're going to have more energy to climb over the fence, right? Collision theory, we increase the temperature of the gas. The particles are moving faster. We have more energetic collisions. The reaction rate is faster. The other thing we can do is to use a catalyst. And a catalyst would be equivalent to either the teacher lifting them up and putting them over, or the teacher taking a couple rails out of this fence and lowering the fence so that it's easier for them to get over. So your book uses a hill analogy. So we've got these, it doesn't really give them a name. We'll call them boulders. So you're trying to get these boulders to fall down this cliff. But there's this hump here. And so you're pushing the boulders up the hill. One way to increase the rate would be to push harder. So just work harder and push harder. That's equivalent to increasing the temperature. Another way is to find a shorter path. Find a shortcut. Find a way around that big hump so that you don't have to go up and over it. That's what a catalyst does. It gives you an alternate pathway, a shortcut. You're playing Candyland, and the catalyst would be one of those little things that you get to skip the whole loop, right? The kids always cheat to get to land on that. And if you're a wise parent, you just let them do it. So back to this type of a graph. Here we have reactants and products. And here's the original activation energy. There's this big hump here. And we can get over it faster by increasing the temperature or increasing the concentrations. Or we can use a catalyst. A catalyst provides an alternate pathway. It lowers the activation energy. Well, let's just a couple things about catalysts. A catalyst participates in the reaction but doesn't get used up. So like the teacher standing at the fence lifting the kindergartners over the fence. You just got one teacher, but one teacher is speeding up that process for lots of children. And when you're done, the teacher's still there. The kids all went over the fence, the teacher's still there. A catalyst does not get used up in an equation. In a reaction. The catalyst is still there. The other thing is that the catalyst does not affect the position of the equilibrium. It just affects how fast you get there. So you've got the forward reaction, the reverse reaction. If we go with the kindergartners, then we have kindergartners also climbing over the fence coming back. Don't know why. I don't know why they went over in the first place, but the catalyst affects the rate of the reaction in one direction. And the reverse reaction is still occurring, and you'll still get to the same point of equilibrium, but it'll just happen faster. So enzymes are biological catalysts. You have probably an uncountable number of chemical reactions occurring in your body right now. And your body is at a particular temperature, right? It's 98.6 degrees Fahrenheit, give or take a couple of degrees. But if you go much higher or much lower, you die, right? If your temperature drops too low, hypothermia, you die. If your temperature goes too high, you have heat stroke, and you die. Okay? So the reactions that occur in a living organism, if we need to speed it up, we can't speed it up by heating things up for a variety of reasons. But one of them is that many reactants are thermally sensitive. If you warm them up, they will actually break apart. Or they might undergo other reactions that you don't want. But you can't just use temperature to control the rate of the reaction. So what your body does, which is just pure genius, is it uses catalysts. So you need to digest something and the reaction's too slow, your body puts out a catalyst that speeds that up for you. Enzymes are the word that we use to describe those biological catalysts, and they increase the rates of biochemical reactions. So here's an example. Enzymes typically have in their name ends in ASE. And then the rest of their name is related to the process that they catalyze. So sucrase is an enzyme that catalyzes the metabolism of sucrose. Sucrose is a disaccharide. It's got two sugars bonded together, a fructose and a glucose. And your body needs to take them apart so that you can use them for other things. Well, there's an activation energy. There's a bond here. And that bond takes energy to break. What sucrase does is it lowers the energy, the activation energy, and makes it easier for the bond to break. And so it speeds up the reaction of breaking the sucrose into its monosaccharides, glucose and fructose. And here's an illustration. This is not what it actually looks like, but it's an idea. So the enzyme is this blue blobby mess here. And enzymes have active sites. And so it's like a little pocket here where the molecule that they act on can come and kind of dock. It's like a docking station. So this is the Death Star. And this is, Luke Skywalker's X-Wing fighter or something, I don't know. Anyway, it comes and docks here. And it docks because of the relationships between the atoms in the enzyme and the atoms in this molecule. And it fits in there nicely. It's like a comfortable seat. And then the other part of it is over here. And when it fits in there, it kind of bends it and stretches it a little bit and causes this bond to be weaker. It puts some stress on this bond. It doesn't break the bond, but it makes it easier for the bond to break. So then this bond breaks, and then the sucrase says, okay, and presses the eject button and shoots that one off. And then another sucrose molecule is enticed in here by this comfy-looking seat and gets kind of stretched and broken in half and then kicked out. Over and over and over and over again. One sucrase molecule, this enzyme, catalyzes this reaction over and over and over again. The sucrase does not get used up. It just keeps going. It lowers the activation energy for the reaction and increases the rate of the reaction. And then your body has, it's really fascinating. It's biochemistry or biological chemistry. And if you're interested in this sort of thing, you can go on and study it. But, we know a lot about all these different processes that occur in your body. And your body uses hormones and other different factors to control the reactions. So, your blood sugar is getting low. And it sends out things that signal the enzymes, that cause the enzymes to catalyze the reaction. It's just incredibly complicated. So your blood sugar, your glucose level in your blood's getting low, and your body stimulates chemical reactions to put more glucose into your blood. You got too much, it sends out something else and gets rid of it. It's really, really amazing. And that's the end of chapter 15. So then we have all these chapter and review things. There's really not that many of them for chapter 15. And those are the chemical skills, things you should be able to do.